Andromeda is the most distant object most people will ever see without a telescope, and the light reaching an eye tonight left it 2.5 million years ago, long before anything resembling a human being existed on Earth. It looks like a faint smudge near the constellation Cassiopeia, barely a fraction of a degree wide, and yet what it actually shows is a second galaxy, 1,000,000,000,000 stars strong, tilted at an angle so steep that most of its light never reaches us at all. The question of how long it would take to cross it sounds simple. It is not. The honest answer depends entirely on what is doing the crossing. A beam of light, a spacecraft built by human hands, a traveller moving close enough to the speed of light for time itself to bend, or the two galaxies themselves, which have already started the job, 4.5 billion years ahead of any ship that might follow. 4 different travellers, 4 different clocks, and 4 completely different numbers, all of them true at once. The night sky holds exactly one object beyond the Milky Way that an unaided human eye can reliably find, a pale, elongated haze hanging near the constellation Cassiopeia, faint enough that city light erases it completely and dark enough, under a clear rural sky, to be mistaken for a stray cloud. That haze is the Andromeda Galaxy, and its faintness is the first clue to how large it actually is. Spread across the sky, Andromeda's true disk covers an area about 6 times the width of the full moon, but almost all of that light is spread so thin across such a wide area that only its dense central bulge gathers enough brightness per patch of sky to register as anything at all. A person looking at Andromeda with the naked eye is seeing perhaps 1% of the galaxy that is actually there. What is actually there, based on decades of measurement using the brightness cycles of certain pulsing stars called Cepheid variables, whose regular dimming and brightening reveals their true distance with unusual precision, is a spiral galaxy roughly 200,000 light-years across, edge to edge. A light-year is not a measure of time but of distance, the distance a beam of light covers in 1 year, travelling at 300,000 kilometres every second, which works out to roughly 9.5 trillion kilometres. 200,000 of those, laid end to end, is the diameter astronomers currently favour for Andromeda's full stellar disk, though the outer edges of any galaxy fade so gradually into surrounding space that the exact boundary is itself a matter of definition, a problem this account returns to later. For comparison, the Milky Way, the galaxy that holds the Earth, Sun, and every star visible without a telescope, spans roughly 100,000 light-years, perhaps a little more. Andromeda is not a small companion smudge in the sky. It is very likely the largest member of the small cluster of galaxies our own Milky Way belongs to, a group of roughly 100 galaxies called the Local Group, most of them small and faint, a handful large enough to matter. The Cepheid method itself deserves a moment's attention, because it is the quiet foundation underneath every distance figure in this account. In the early 20th century, the American astronomer Henrietta Swan Leavitt, studying thousands of variable stars photographed at the Harvard College Observatory, noticed that Cepheid variables with longer pulsing periods were reliably brighter than ones with shorter periods, a relationship precise enough to work backward. Measure how fast a Cepheid pulses, and its true brightness becomes known, and comparing that true brightness to how dim it actually appears from Earth reveals exactly how far away it must be. Edwin Hubble later used exactly this technique, applied to Cepheids inside the Andromeda Nebula, to prove in the 1920s that Andromeda was not a cloud of gas inside the Milky Way at all, as many astronomers had assumed, but an entirely separate galaxy sitting far beyond the Milky Way's own edge. That discovery, barely a century old, is the reason this account can even describe Andromeda as a second galaxy in the first place, rather than a nearby smear of glowing gas. The distance separating the two spiral giants is itself almost too large to hold in mind using ordinary units, which is why astronomers reach for the light-year instead of the kilometre the moment the numbers grow large enough. Andromeda sits about 2.5 million light-years from Earth. That distance means the light striking a retina on a clear night tonight left Andromeda's stars 2.5 million years ago, arriving now only because it has been travelling uninterrupted at the fastest speed anything can travel for the entire span of that time. To put that duration beside something human-scaled, 2.5 million years ago, no member of the genus Homo had yet evolved into anything resembling the species reading or hearing this now. Stone tools were just beginning to appear in East Africa, crafted by early hominins whose brains were roughly a third the size of a modern human's. Every photon forming that pale smudge overhead left its source before that tool-making began, and has been in transit alone, through the near-perfect vacuum of intergalactic space ever since, passing nothing, slowed by nothing, arriving finally at a planet that did not yet exist with anyone capable of noticing it. A fair question follows immediately from these two numbers: the size of the galaxy and the distance to it. If that galaxy is really 200,000 light-years wide, and its light takes 2.5 million years just to arrive, how long would it take to actually cross it, to travel from one edge of that great disk to the other? That is the question this account exists to answer honestly, and the first surprise is that there is no single honest answer. There are several, and they disagree with each other by factors of thousands, because they describe entirely different kinds of journey. One belongs to light, which is already making the crossing constantly indifferent to it. One belongs to any spacecraft humanity might someday build, bound by fuel, mass and the hard limits of propulsion. One belongs to a hypothetical traveller moving close enough to light speed that time itself begins behaving unfamiliarly, and one belongs to the galaxies themselves, which are not standing still relative to one another at all, and have, in a sense that will become literal by the middle of this account, already begun their own crossing of each other. Before any of those answers can be compared fairly, the unit doing all the work in this story needs to be understood properly, not as a poetic phrase, but as an exact measurement. That is where the next chapter starts, with the light year itself, and with what it actually means to say that something is a certain number of years away. A light year sounds like it should measure time, and the confusion is understandable, since the word carries the word year inside it. It measures distance. Specifically, it is the distance a beam of light travels in a single year, moving through the vacuum of space at 300,000 kilometers every second, a speed nothing with mass can ever reach or exceed, so far as current physics has ever found an exception to. Multiply that speed across the roughly 31.5 million seconds in a year, and the result is about 9.5 trillion kilometers. That is one light year, not a duration, but a very long ruler, built out of a duration, because no ordinary ruler is long enough to be useful once distances stop fitting inside a single solar system. It helps to build that ruler up from something familiar first. Light from the sun takes about 8 minutes to reach Earth, a fact many people already know, which makes the sun 8 light minutes away. Light from the next nearest star system, Proxima Centauri, takes about 4 years and 2 months, making it a little over 4 light years away, a distance Chapter 4 returns to in more detail. Light from the center of the Milky Way takes about 26,000 years, and light from Andromeda takes 2.5 million years. Each step up multiplies the previous distance by a factor of thousands, which is part of why intuition, trained entirely on distances a human body can walk, drive or fly across in a lifetime, simply has nothing to grab onto once the numbers reach galactic scale. The only way through is arithmetic, not imagination. Once that ruler exists, the numbers describing Andromeda stop being abstractions and start behaving like an itinerary. The Andromeda Galaxy's disk spans roughly 200,000 light-years, so a single beam of light, entering one edge of that disk and travelling in a straight line to the opposite edge, needs roughly 200,000 years to make the trip, since a light-year is, by definition, exactly the distance light covers in a year. 200,000 years is longer than the entire existence of anatomically modern humans, currently estimated at around 300,000 years at the very outside and often placed closer to 200,000, depending on which fossil evidence is weighted most heavily. Light, moving at the one true speed limit the universe enforces without exception, would need a span of time roughly comparable to the entire span of human existence just to cross one galaxy's disk without once slowing down, stopping, or being obstructed. It helps to hold two separate numbers apart here, because this account will use both constantly, and they are easy to blur together. The first is the distance to Andromeda, about 2.5 million light-years, which describes how long light takes to travel from Andromeda to Earth. The second is the width of Andromeda itself, about 200,000 light-years, which describes how long light takes to travel across the galaxy once it is already there. The first number is roughly 12 times larger than the second. A useful way to hold this in mind: getting to Andromeda, for any traveller, light included, is a far larger undertaking than getting across it once you have arrived. Everything this account calculates from here forward keeps that distinction in view, because most casual descriptions of galactic distances collapse it, and the collapse is exactly where the myths start. One of those myths deserves addressing directly, since it recurs constantly in casual conversation about deep space. The idea that looking at something very far away means looking at ancient, dead information with nothing left to say about the present. That framing is not wrong, exactly, but it flattens something genuinely strange. When a person looks at Andromeda tonight, they are not seeing one single moment frozen in time. They are seeing light that left different stars on different sides of that vast disk at slightly different times, all arriving at the same instant, simply because it has all had time to finish its individual, honest 2.5 million year journey. The near edge of the galaxy's light left a little more recently than the far edge's light, by up to 200,000 years, the very same span of time light needs to cross the whole disk. The Andromeda a person sees is therefore not a single snapshot but a thin slice sampled unevenly across 200,000 years of that galaxy's own history, compressed by geometry into what looks, from here, like one simultaneous picture. The same layering applies at a smaller scale to every star inside Andromeda that a large telescope resolves individually. A star near Andromeda's core and a star at the far outer edge of its disk are both showing light from moments separated by up to 200,000 years, even though both appear in the very same photograph, taken at the very same instant by the very same instrument on Earth. No image of Andromeda has ever shown, or could ever show, the galaxy as it exists at any single moment. It shows a composite stitched together by light that all happened to finish arriving on the same night, having started its journey across a span of time, as long as light itself needs to cross the object being photographed. With the ruler established and light's own crossing time fixed at roughly 200,000 years, the natural next question is how that compares to anything humanity has actually built and launched. The answer, it turns out, is not a matter of being merely slower. It is a matter of being slower by a margin so large that ordinary comparison starts to break down, which is exactly where the next chapter goes. Humanity has built exactly one object fast enough to earn the title of fastest thing ever launched from Earth. The Parker Solar Probe, a NASA spacecraft that dives repeatedly close to the Sun, using the Sun's own gravity to accelerate itself on each pass. At its closest approaches, it reaches speeds of roughly 690,000 kilometers per hour, or about 192 kilometers every second, fast enough to travel from New York to Tokyo in under a minute. That speed is achieved only briefly, only near the Sun, and only because the spacecraft is falling, not flying under its own power, but it remains the honest record holder, well ahead of the Voyager probes, humanity's most distant travelers, which cruise through interstellar space at a comparatively modest 17 kilometers per second, and well ahead too of missions like New Horizons, which sped past Pluto in 2015 at roughly 14 kilometers per second, or Juno, orbiting Jupiter at speeds that briefly touch 70 kilometers per second during its closest passes, borrowed from Jupiter's own immense gravity in much the same way Parker borrows speed from the Sun. Set either of those speeds against light's own 300,000 kilometers per second, and the gap becomes clear even before any distance enters the calculation. The Parker Solar Probe's peak speed is a little under 1/15 of 1% of the speed of light. Voyager 1, humanity's farthest travelling object, moves at roughly 1/17,000th of the speed of light. Neither spacecraft is remotely close to the regime where crossing a galaxy the size of Andromeda becomes even a distant possibility within a human lifetime, or within the lifetime of a civilization, or within the lifetime of a star. The actual numbers make the gap concrete rather than merely rhetorical. Light crosses Andromeda's 200,000 light-year disk in about 200,000 years. At Parker Solar Probe's peak speed, sustained indefinitely, which is itself physically impossible since that speed depends on a close pass by the Sun's gravity, the same crossing would take roughly 150 million years. At Voyager 1's steady interstellar cruising speed, it would take closer to 3.5 billion years, longer than the age of complex life on Earth, and not far short of the age of the Earth itself, at roughly 4.5 billion years. To place the Parker Solar Probe figure beside something else familiar, the universe itself, according to the best current measurements of the cosmic microwave background, the faint afterglow of the Big Bang, is about 13.8 billion years old. 150 million years is a small fraction of that age, but it is still roughly 11,000 times longer than the entire span of recorded human history, which stretches back only about 5,000 years to the earliest known writing systems. A fair objection follows naturally. Engineering improves, and comparing today's fastest probe to a 200,000 light-year journey ignores centuries of future progress. That objection is reasonable, and this account takes it seriously, rather than dismissing it, which is why a later chapter deals directly with the physics of pushing a spacecraft toward a meaningful fraction of the speed of light, and with exactly why that physics resists brute force improvement in a way that, say, aircraft speed or computer processing power never did. Aircraft speed improved because engineers found better ways to burn the same basic kind of chemical fuel more efficiently, and computer processing power improved because transistors could simply be made smaller, packing more of them into the same space. Neither kind of improvement has an equivalent waiting to be discovered for propulsion at relativistic speeds, because the limiting factor there is not manufacturing cleverness, but the raw amount of energy required, a distinction the next chapter examines closely. Even granting decades or centuries of hypothetical future propulsion breakthroughs, the gap explored in this chapter is worth sitting with honestly first, because it is the gap that makes interstellar and intergalactic travel, as commonly imagined in fiction, so different from the reality current physics describes. The distances are not merely large, they are large enough that even genuinely record-breaking human engineering barely moves the needle against them. If the entire history of spaceflight since 1957, when the first artificial satellite reached orbit, were compressed into a single continuous improvement in top speed, extended forward for another 1,000 years at the same rate of progress, the resulting speed would still fall enormously short of what a genuine galaxy crossing on any human timescale would actually require. That gap between engineered speed and galactic distance raises a second, quieter problem that has nothing to do with speed at all. What a spacecraft would actually encounter along the way, assuming it somehow closed that gap. Popular imagination tends to picture a galaxy crossing as a hazardous obstacle course, weaving between stars and dodging debris. The truth, as the next chapter shows, is almost the opposite, and understanding it matters for everything that follows. A spiral galaxy like Andromeda or the Milky Way has a recognizable structure, a dense central bulge of older, tightly packed stars, a flat rotating disk spiraling outward from that bulge in great curving arms rich with younger stars and the gas clouds that form them, and a much larger, much fainter halo of ancient stars and star clusters surrounding the whole structure like a thin, spherical shell. Photographs of galaxies, especially the long-exposure kind, favoured by astronomy magazines, tend to show this structure as a solid, luminous object, and that impression is almost entirely an artifact of the exposure length and the eye's inability to judge scale from a flat image. A galaxy, examined honestly, is overwhelmingly empty space with a light dusting of stars floating through it. The distances between individual stars, even within a galaxy's crowded central disk, are almost incomprehensibly large next to the stars themselves. The nearest known star to the Sun, a small, dim red star called Proxima Centauri, sits about 4.2 light-years away, a distance of roughly 40 trillion kilometers. To make that number feel physical rather than merely large, imagine shrinking the Sun down to the size of a grain of sand roughly 1 millimeter across. On that scale, Earth would orbit that grain of sand at a distance of about 11 centimeters, and Proxima Centauri, the single closest star in the entire universe to our own, would still sit more than 4 kilometers away, with essentially nothing but empty space, no other grains of sand, filling every bit of that distance, and the region around the Sun is, if anything, slightly more crowded with stars than the galactic average, since the Sun sits within the disk rather than out in the sparser halo. This emptiness has a direct and important consequence for the idea of crossing a galaxy. A straight line drawn through Andromeda's disk, from one edge to the other, would very likely pass nowhere near an actual star. Estimates of stellar density in a typical galactic disk put the average spacing between neighbouring stars at several light-years, meaning a 200,000 light-year line crosses an enormous stretch of genuinely empty space, punctuated only occasionally, and unpredictably, by anything solid at all. Even in the densest parts of a galaxy's central bulge, where stars are packed together far more tightly than out in the spiral arms, the average gap between neighbours is still measured in fractions of a light-year, rather than anything a spacecraft could accidentally strike. The popular image of a spaceship weaving between densely packed stars, banking around suns like obstacles in an asteroid field, describes essentially no real region of any galaxy ever measured. The far more accurate image is a line drawn through open water, with the stars themselves scattered as rarely, relative to the scale of the crossing, as isolated buoys across an entire ocean. This is worth stating plainly, because it corrects a genuinely common misconception, related to but distinct from the well-known myth about the asteroid belt within our own solar system, which is often imagined as a dense field of tumbling rocks, when the reality is that neighbouring asteroids typically sit hundreds of thousands of kilometres apart, easily crossed by spacecraft without any need for evasive manoeuvring. Several probes, including Galileo, New Horizons and Dawn, have already flown through the asteroid belt without incident and without ever coming close to an accidental collision. The same basic correction, scaled up enormously, applies to crossing a galaxy. Space at every scale examined so far in this account, from the gaps between planets to the gaps between stars, is defined far more by what is absent from it than by what is present in it. It is worth quantifying just how little of a galaxy's volume its stars actually occupy. If every star in the Milky Way, roughly 100 to 400 billion of them depending on how the fainter, harder to count red dwarfs are estimated, were represented by a single grain of sand, and those grains were scattered through a volume matching the galaxy's true disk at the same relative scale, the resulting cloud of sand would be so thin that a traveller moving through it in a straight line would need to cross a distance equivalent to thousands of kilometres of empty air, on average, between each grain encountered. Multiply that same thinness across the full width of a galaxy, and it becomes clear why the danger in a hypothetical crossing was never going to be collision. The genuine difficulty, as later chapters return to, is not steering around anything. It is simply enduring the distance. That emptiness matters directly for the question this account is built around, because it means the difficulty of crossing Andromeda has nothing to do with navigating around obstacles, and everything to do with the sheer scale of the emptiness itself. A traveller crossing Andromeda would not need to dodge anything. They would simply need to survive and continue moving across 200,000 light-years of open, nearly featureless dark for as long as their journey required. How long that journey would feel, from the traveller's own point of view, turns out to depend on something stranger than distance and speed alone. The traveller's own speed changes the traveller's own experience of time. That is the subject the next chapter takes on directly. Nothing discussed so far changes the basic arithmetic. Distance divided by speed gives time, and at any speed short of light itself, crossing 200,000 light-years takes at least 200,000 years, measured from the reference point of someone standing still and watching the whole trip unfold. But Albert Einstein's theory of special relativity, developed in 1905 and confirmed by more than a century of subsequent experiment, describes something genuinely counterintuitive about that arithmetic. It depends entirely on who is doing the measuring. Time does not pass at the same rate for every observer. It passes more slowly, from an outside point of view, for anything moving very fast relative to that outside observer, an effect called time dilation. The effect is not a philosophical curiosity or a rounding error. It has been measured directly, repeatedly, using atomic clocks flown on aircraft and orbiting satellites. In one famous 1971 experiment, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks around the world on commercial airliners, once eastward and once westward, and compared them afterward against a stationary reference clock. The flown clocks had genuinely ticked a different number of nanoseconds than the one left on the ground, exactly matching relativity's prediction. The effect must be corrected for constantly in the operation of GPS satellites, whose onboard clocks run measurably faster than clocks on the ground, owing to a combination of their speed and their altitude, by an amount that would otherwise introduce location errors of several kilometers per day, if left uncorrected. Time dilation is not a hypothesis awaiting confirmation. It is an engineering fact, built into the systems billions of people rely on every day without realizing it. The effect grows dramatically as speed approaches the speed of light, in a way that stays negligible at ordinary speeds, and becomes overwhelming near the cosmic limit. A traveller moving at half the speed of light would experience time passing at roughly 87% of the rate experienced by someone standing still. A traveller moving at 99.5% of the speed of light would experience time passing at roughly 1/10 that outside rate. For every 10 years that passed for the people left behind, only about 1 year would pass for the traveller. Push the speed still closer to light's own, to 99.99%, and the ratio grows past 100 to 1. At 99.9999% of the speed of light, a speed no known technology comes close to achieving, but which is not forbidden by the mathematics itself, the ratio climbs past 700 to 1. There is no upper limit to how extreme this ratio can become as speed approaches, without ever quite reaching the speed of light itself, which no object with mass can attain. Applied to a hypothetical crossing of Andromeda, this effect produces a strange and genuinely accurate split between two honest answers to the same question, and the split is exactly why this account keeps insisting there is no single correct duration for such a trip. From the point of view of everyone who stayed behind, watching from Earth or from Andromeda, the crossing would take at minimum the roughly 200,000 years that light itself needs. Since nothing with mass can travel faster than light, and a real ship, even an extraordinarily fast one, would need somewhat longer than light does. But from the point of view of a traveller aboard a ship moving close enough to the speed of light, their own onboard clock, their own lived experience, their own aging body might register only a few thousand years, or at truly extreme and almost certainly unreachable speeds, conceivably far less. At 99.995% of the speed of light, for instance, the roughly 200,000-year outside crossing would be experienced by the traveller as lasting only around 2,000 years, still longer than all of recorded human history, but a full 100 times shorter than the outside figure. This relativistic shrinking has a curious mirror image description that some physicists find more intuitive. From the traveller's own point of view, it is not that their clock slows down, but that the distance itself shrinks, an effect called length contraction, which is mathematically equivalent to time dilation, but describes the same physics from the traveller's own frame rather than the outside observer's. A traveller moving at 99.995% of the speed of light would measure Andromeda's own disk, in the direction of travel, as being only about 2,000 light-years wide rather than 200,000, compressed by their own extreme velocity. Neither description is more correct than the other. They are the same journey, described from two different, equally valid vantage points, and both agree perfectly on what the traveller would actually experience upon arrival. This is real physics, verified physics, not speculation borrowed from fiction, and it changes the emotional shape of the question this account is asking. It is not that crossing Andromeda is simply, uniformly, 200,000 years long. It is that the number 200,000 belongs to the people who stay, while an entirely different, potentially much smaller number could belong to anyone who actually made the trip, if such a trip were ever attempted. Whether such a trip could ever actually be attempted, however, is a separate question from whether relativity permits it in principle, and the honest answer to that separate question is considerably less encouraging. That is where the next chapter goes. The time dilation effect described in the previous chapter might seem to offer a shortcut. Build a ship fast enough, and the crossing collapses from 200,000 years down to something a human crew could survive. The physics permitting that shortcut is real. The physics required to build such a ship is where the idea runs into a wall that has resisted every proposed solution for the better part of a century, and the wall is not a matter of insufficiently advanced engineering. It is a matter of energy, and the amount required grows in a way that punishes every added increment of speed more severely than the last. Accelerating any object with mass requires energy, and the energy required to reach a given speed rises according to well-established physics that most people encounter first in a basic mechanics class. Kinetic energy grows with the square of speed, so doubling a spacecraft's speed requires roughly 4 times the energy, not twice. That relationship alone makes high speeds expensive. Relativity adds a second, steeper penalty on top of it. As an object's speed approaches the speed of light, its effective mass, from the point of view of an outside observer, increases as well, meaning each further increment of speed costs not just more energy per the ordinary formula, but progressively more energy than that ordinary formula alone would predict, with the required energy formally becoming infinite as speed approaches light's own, exactly, which is the underlying reason nothing with mass can ever actually reach it. Translated into concrete terms, the energy required to accelerate even a modestly sized spacecraft to a meaningful fraction of light speed is staggering. A rough calculation for a 1-ton payload reaching 90% of the speed of light calls for an amount of energy comparable to several minutes of the sun's total energy output, a star that radiates more energy in 1 second than humanity has generated across its entire recorded history. To place that figure beside something more familiar still, The entire estimated global energy consumption of human civilization across a full year, from every power plant, engine and furnace on the planet combined, would need to be multiplied many tens of thousands of times over to match the energy required for that single 1-ton spacecraft's acceleration. No chemical rocket and no currently demonstrated propulsion technology produces anything remotely close to that kind of energy density, and even speculative concepts studied seriously by physicists, such as antimatter engines or Bussard-style ramjets that scoop up interstellar hydrogen for fuel, run into severe practical problems of their own. Antimatter cannot currently be produced or stored in anything beyond microscopic quantities, at a cost measured in trillions of dollars per gram by the most optimistic projections, and interstellar hydrogen is spread too thin, at roughly 1 atom per cubic centimetre in the densest nearby regions, to scoop effectively at any realistic collecting speed, without the scoop itself creating more drag than thrust. There is also a second obstacle layered on top of the energy problem, one engineers call the rocket equation problem. A spacecraft must carry its own fuel, and that fuel itself has mass, which then itself needs to be accelerated, which then requires still more fuel to accelerate the fuel, in a spiral that grows exponentially worse as the target speed increases. This relationship, formalized by the Russian scientist Konstantin Tsiolkovsky in 1903, and still the starting point for every real mission planning calculation NASA and other space agencies perform today, is precisely why no realistic chemical or even nuclear-powered rocket design gets remotely close to relativistic speeds using fuel it carries aboard from the start. The fuel mass required becomes larger than the observable universe long before the ship approaches any fraction of light speed worth mentioning. Serious proposals for interstellar travel generally abandon the idea of carried fuel entirely, favouring concepts like light sails pushed from outside by enormous ground-based or orbital laser arrays, an idea studied under projects such as Breakthrough Starshot, aimed at tiny gram-scale probes rather than crewed ships, targeting roughly 20% of the speed of light for a journey to the nearest star system, Alpha Centauri, a target still 4 orders of magnitude closer than Andromeda. Even Breakthrough Starshot's modest ambitions illustrate the scale of the underlying problem. Propelling a probe weighing about as much as a paperclip to 20% of light speed is projected to require a ground-based laser array with a combined output on the order of 100 gigawatts, focused for only a few minutes, roughly comparable to the output of 100 large nuclear power stations running simultaneously. And the project remains, decades after its 2016 announcement, in the research and feasibility stage rather than active construction. Scaling that same basic approach up from a paperclip weight probe to anything resembling a ship capable of carrying a human crew and pushing its target speed higher still to make an intergalactic crossing survivable within a human lifetime multiplies the already extreme energy requirement by factors large enough that no credible engineering roadmap currently proposes it, even as a distant, centuries-away ambition. None of this means relativistic travel is forbidden by physics in the way that travelling faster than light itself is forbidden. It means the energy and engineering demands scale so steeply that no currently known or seriously proposed technology gets within many orders of magnitude of what an actual Andromeda crossing, even at a survivable fraction of light speed, would require. The gap explored in the earlier chapter comparing Voyager and Parker Solar Probe to the speed of light was not a temporary gap awaiting the next few centuries of engineering progress. It is a gap rooted in the same physics that makes light speed itself an absolute limit, and there is no known path around it using any principal physics currently accepts as sound. With both the speed problem and the energy problem laid out honestly, the next reasonable question shifts away from how fast a ship could go, and toward a much older, quieter problem this account has been setting aside since the first chapter. What, precisely, counts as the edge of a galaxy in the first place? The answer changes the size of the crossing itself, sometimes dramatically, and it is not a settled number in the way the previous chapters may have implied. Every number in this account so far has treated Andromeda's diameter as a fixed known quantity, roughly 200,000 light-years across. That number describes the visible stellar disk, the flattened, spiraling structure that shows up clearly in photographs, and that most people picture when they hear the word galaxy. It is a reasonable working definition, and it is also, honestly, an arbitrary one, chosen because it corresponds to where the disk's light becomes too faint to easily distinguish from the general dark background of space. Galaxies do not have hard edges the way a planet or a building does. They fade. Beyond the visible disk, both Andromeda and the Milky Way are surrounded by a much larger, much sparser stellar halo, a roughly spherical region containing ancient star clusters and scattered individual stars, far less densely packed than the disk, extending outward for a considerable distance before finally thinning into the near-total emptiness of intergalactic space. Andromeda's stellar halo has been mapped in unusual detail by a survey called PANDAS, the Pan-Andromeda Archaeological Survey, conducted using the Canada-France-Hawaii telescope, which traced faint individual stars far beyond the visible disk and found streams and clumps of stars, likely the shredded remains of smaller satellite galaxies that Andromeda has consumed over billions of years, extending out to hundreds of thousands of light-years from the galaxy's center. Beyond even that halo, and detectable only through its gravitational effects rather than any light it emits, lies something stranger still, a vast halo of dark matter, a form of matter that does not emit, absorb, or reflect light and has never been directly observed, but whose gravitational influence is required to explain why galaxies rotate the way they do, holding their outer stars in orbit at speeds too fast to be explained by the visible matter alone, a discrepancy first noticed clearly in detailed studies by the American astronomer Vera Rubin in the 1970s. Rubin, working with instrument maker Kent Ford, measured how fast stars orbited at different distances from the centers of dozens of spiral galaxies, and found that stars far out in a galaxy's disk were orbiting just as fast as stars much closer in, when ordinary gravity, sourced only by the visible stars and gas, predicted the outer stars should be orbiting much more slowly, the same way outer planets in the solar system orbit the sun more slowly than inner ones. The only way to explain the observed speeds was to assume a large amount of additional invisible mass surrounding each galaxy, an idea that had been proposed decades earlier by the Swiss astronomer Fritz Zwicky studying galaxy clusters, but which Rubin's stellar orbit measurements made difficult to dismiss. Current models, built from the way Andromeda's gravity influences its smaller satellite galaxies and the surrounding intergalactic medium, suggest this dark matter halo may extend well over 1 million light-years from Andromeda's center, dwarfing the visible disk by a factor of roughly 5 or more, though the exact boundary remains genuinely uncertain and is an active area of research. Some estimates, built from studying the motion of Andromeda's satellite galaxies far out on its periphery, push the halo's effective edge out past 1.5 million light-years, roughly halfway to the Milky Way itself, though the precise figure depends heavily on which satellite galaxies are included in the calculation, and how their own individual motions are modelled. This matters enormously for the question this account is built around, because how someone chooses to define crossing Andromeda changes the answer by an enormous factor. Crossing the visible, luminous disk means a journey of roughly 200,000 light-years, the number used in every chapter so far. Crossing the full extent of Andromeda's gravitational influence, out through the dark matter halo on one side, and back through it on the other, could mean a journey closer to 2 million light-years or more, 10 times longer, even though almost none of that additional distance would contain anything visible at all. No stars, no light, nothing but the influence of matter that cannot be seen, felt, or detected by any instrument other than its gravity. This is not a flaw in the question. It is a genuine feature of how galaxies are actually built, and it is worth pausing on because it illustrates something true of nearly every large-scale astronomical measurement. Precision often applies only within a chosen definition, and the definition itself is a judgment call rather than a fact handed down by nature. When earlier chapters stated Andromeda's diameter as roughly 200,000 light-years, that figure was never a claim about where the galaxy physically stops. It was a claim about where its light becomes too faint to easily measure. The galaxy itself, in the fullest gravitational sense, is a great deal larger, and by some reasonable definitions, extends far enough that it very nearly touches the Milky Way's own halo already. That last detail is not incidental. It leads directly into the most important reversal in this entire account. The two galaxies are not simply two distant, independent structures separated by 2.5 million light-years of empty space, waiting patiently for some future traveller to bridge the gap between them. Measured carefully, they are already reaching toward each other, and by some definitions their outer halos may have already begun to touch. The next chapter turns to that fact directly, because it changes everything this account has assumed about who, or what, is actually doing the crossing. In the early 20th century, the American astronomer Vesto Slipher, working at Lowell Observatory in Arizona, measured something unexpected about the light coming from Andromeda, then still commonly called the Andromeda Nebula, since its status as a separate galaxy beyond the Milky Way had not yet been established. By analyzing how Andromeda's light was stretched or compressed, a technique that reveals motion by shifting light toward longer, redder wavelengths when an object moves away and toward shorter, bluer wavelengths when it moves closer, an effect known as the Doppler shift, Slipher found that Andromeda's light was shifted toward the blue. That meant, unambiguously, that Andromeda is moving toward the Milky Way, not away from it, at a speed of roughly 110 kilometers every second, a finding later confirmed and refined by generations of subsequent astronomers using increasingly precise instruments, including modern spectrographs capable of measuring that velocity to within a kilometer or two per second. This single measurement quietly overturns the framing this account has used up to this point, in which Andromeda sits as a fixed distant target waiting for some traveller to reach it. Andromeda is not fixed. It is closing the gap. At 110 kilometers per second sustained over cosmic timescales, researchers, most notably a detailed study led by astronomer Roland van der Marel and colleagues using precise measurements from the Hubble Space Telescope, have calculated that Andromeda and the Milky Way are on course to begin merging in roughly 4 to 5 billion years, a timeline the evidence supports with reasonable confidence, though the exact date and even some structural details of the encounter remain subjects of ongoing refinement as measurements improve. Measuring Andromeda's sideways motion across the sky, the component of its movement that determines whether the two galaxies will collide head-on or merely swing past each other, required tracking the galaxy's position with extraordinary precision across roughly a decade of repeated Hubble observations, since that sideways drift amounts to a change smaller than the width of a single pixel in most telescope images spread across many years. 4 to 5 billion years is worth placing beside a familiar number for scale. It is roughly the same span of time that has already passed since the Earth itself formed, about 4.5 billion years ago. The merger between Andromeda and the Milky Way, in other words, will not happen soon on any timescale meaningful to a human life, a human civilization, or even the entire span of human evolutionary history so far. It will happen roughly one Earth age from now, a duration so vast that the Sun itself, as later chapters cover, will have already changed dramatically by the time it arrives. Another way to hold the number: if the entire 13.8 billion year history of the universe since the Big Bang were compressed into a single 24-hour day, the merger would arrive at around 8 o'clock in the evening, with humanity's entire recorded history occupying less than the final thousandth of a second before midnight. What makes this merger different from the earlier chapter's treatment of crossing Andromeda is that it does not involve a single traveller journeying from one edge of the galaxy to the other. It involves the entire galaxy moving as a whole toward another entire galaxy, until the space separating their two disks collapses to nothing, and the structures themselves begin to interpenetrate. The scientific term astronomers sometimes use informally for the eventual combined structure is Milkomeda, a name that captures the basic outcome even though the actual merger, as the next chapter details, unfolds over hundreds of millions of years rather than as a single dramatic event, and produces something structurally quite different from either of its two parent spirals. It is worth noting that Andromeda and the Milky Way are not the only two galaxies involved. The Triangulum Galaxy, a smaller spiral roughly 3 million light-years away, and itself a member of the local group, is also gravitationally bound to Andromeda, and may play a role in the eventual encounter, either merging with Andromeda first, being flung onto a wider orbit by the chaos of the main collision, or merging with the combined Milky Way-Andromeda system at some later stage still, a detail current simulations have not yet fully resolved. The local group, in this sense, is not a static collection of independent galaxies, but a slowly collapsing gravitational system, its largest members drawing inexorably closer together across billions of years, a process astronomers expect will eventually leave a single large elliptical galaxy, where several separate spirals once orbited each other. This reframes the entire question this account opened with. Crossing Andromeda, in the sense the earliest chapters imagined, treating Andromeda as a stationary destination reached by an outbound traveller, may never actually happen, because Andromeda will not remain a separate distinct galaxy indefinitely, waiting to be reached. Long before any spacecraft, real or hypothetical, could complete such a crossing at any technologically plausible speed. The galaxy itself will have already come to the Milky Way, and the two will have begun the long process of becoming one. The next chapter examines what that process actually looks like up close, and answers a question that follows naturally from everything established in the earlier chapters about how empty a galaxy actually is. When two galaxies collide, do any stars within them actually collide with each other? The word merger, applied to two galaxies each containing hundreds of billions of stars, understandably conjures an image of violent, widespread collision. Stars striking stars, solar systems torn apart in direct impacts, a chaotic wreckage of destroyed worlds. That image, built largely from science fiction rather than astrophysics, turns out to be almost entirely wrong, and the reason traces directly back to the emptiness described earlier in this account. Stars within a galaxy are separated, on average, by several light-years of open space, a distance so enormous relative to the stars themselves that even when two entire galaxies pass through each other, the odds of any two individual stars colliding directly remain, by most current estimates, close to zero throughout the entire encounter. What does happen, and what makes the merger a genuinely dramatic and transformative event, despite the near absence of direct stellar collisions, is gravitational. As Andromeda and the Milky Way approach and begin to interpenetrate, the immense combined gravity of each galaxy's hundreds of billions of stars, along with their much larger dark matter halos, begins distorting the other galaxy's structure long before the two disks actually overlap. Spiral arms stretch and unwind. Long, faint streams of stars called tidal tails are pulled out from each galaxy's disk by the other's gravity, sometimes stretching for hundreds of thousands of light years, longer than either galaxy's own diameter. Astronomers have observed exactly this kind of distortion happening in other, more distant galaxy pairs already caught mid-merger, most famously the Antennae galaxies, a pair of colliding spirals roughly 45 million light-years away whose two long curving tidal tails, resembling a pair of insect antennae in wide-field images, gave the pair its popular name, giving reasonably strong confidence in how the Andromeda and Milky Way encounter will likely unfold, even though the process here on Earth remains billions of years in the future. Gas is affected far more violently than stars, because unlike stars, clouds of interstellar gas genuinely do collide, compress, and shock against each other when two galaxies interpenetrate. Where these gas clouds crash together, they compress dramatically, and compressed gas is exactly the raw material new stars form from. Observations of merging galaxies elsewhere in the universe consistently show intense bursts of new star formation, triggered by exactly this kind of gas compression, sometimes producing new stars at many times the ordinary rate for a quiet, undisturbed spiral galaxy, a phenomenon astronomers call a starburst. Some of the most extreme starburst galaxies observed, thought to be in the advanced stages of a major merger, form new stars at rates hundreds of times faster than the Milky Way's own fairly modest pace of roughly 1 or 2 new stars per year. It is a strange asymmetry worth sitting with. A galactic merger that leaves nearly every individual star's immediate neighborhood undisturbed can still trigger the birth of enormous numbers of brand new stars elsewhere in the same encounter, entirely through the collision of gas rather than the collision of stars. The process is not a single violent night but a long repeated series of passes. Current models suggest Andromeda and the Milky Way will not simply merge in one clean pass. They will likely swing past each other, pulled back by mutual gravity, pass through each other again, and repeat this gravitational give and take across hundreds of millions of years, before finally settling into a single combined structure. Some simulations suggest the first close pass could occur roughly 4 billion years from now, with the two galactic cores not fully coalescing into a single object until perhaps 6 or 7 billion years from now, several billion years further out than the first noticeable disturbance. Repeated close passes like this progressively strip both galaxies of their original spiral shape, since the ordered, rotating disk structure that produces spiral arms is gradually scrambled by each successive gravitational disturbance. Simulations of the eventual Milky structure generally predict the end result will not be a larger spiral at all, but a smoother, rounder elliptical galaxy, the shape astronomers typically associate with the aftermath of a completed galactic merger, its stars orbiting in far less orderly paths than the clean rotating disk either parent galaxy once had. There is also the matter of the two galaxies' central supermassive black holes. Andromeda's, estimated at around 100 million times the mass of the Sun, and the Milky Way's own, called Sagittarius A star, at a comparatively modest 4 million solar masses. Current models predict that as the merger completes, these two black holes will sink toward the center of the newly combined galaxy through a process called dynamical friction, gradually losing energy to the surrounding stars and gas, before eventually spiraling together and merging into a single, far larger black hole themselves, likely releasing a brief but immense burst of gravitational waves, ripples in spacetime itself, in the final moments of that black hole merger, an event similar in kind, though vastly larger in scale, to the smaller black hole mergers already directly detected by gravitational wave observatories on Earth since 2015. So the eventual union of Andromeda and the Milky Way, despite the word merger implying a single decisive event, plays out as a slow, repeated, gravity-driven process stretched across hundreds of millions of years, during which the individual stars each parent galaxy contains remain, overwhelmingly, exactly as untouched by direct collision as they always were. What changes is the shape, the structure, and eventually the identity of both galaxies as distinct objects. What that means for anything living within either galaxy while all this unfolds, including, hypothetically, anything still living in the Milky Way's own solar system, is the next honest question to ask, and it leads somewhere less encouraging than the merger's relative gentleness toward individual stars might suggest. Every timescale in this account so far has treated 4 to 5 billion years as the relevant horizon, the point at which Andromeda and the Milky Way begin merging in earnest. It is worth asking directly what else is expected to happen across that same span of time, because the answer changes how this whole story should be understood, particularly with respect to whether anything from Earth could ever actually witness, let alone participate in, the eventual crossing this account has spent so long calculating. The Sun, like all stars, is slowly changing as it ages, becoming gradually brighter over time as the nuclear fusion reactions in its core, which convert hydrogen into helium and release the energy that becomes sunlight, adjust to the changing composition of the core over billions of years. As hydrogen is steadily used up, the core very slowly contracts and heats, and the fusion rate climbs in response, meaning the Sun today is already roughly 30% brighter than it was when it first ignited about 4.6 billion years ago. And it will continue brightening at an accelerating pace from here. Current astrophysical models suggest the Sun's steadily increasing brightness will raise Earth's surface temperature enough to boil away its oceans in roughly 1 billion years, an event sometimes called the moist greenhouse or runaway greenhouse threshold. Long before the Sun undergoes any of the more dramatic later life changes it is popularly known for. 1 billion years is a large number, but it is a small fraction of the 4 to 5 billion years the galactic merger requires to begin, meaning that by the time Andromeda and the Milky Way are even approaching the start of their long gravitational entanglement, Earth is expected, on current models, to have already been uninhabitable for roughly 3 or 4 billion years. Later still, roughly 5 billion years from now, close to the same era the merger is expected to be well underway, the Sun is expected to exhaust the hydrogen fuel in its core and begin a dramatic transformation into a red giant, swelling enormously as its outer layers expand, while its core contracts and heats further, eventually reaching a diameter perhaps 200 times its current size, likely engulfing Mercury and Venus, and possibly reaching close enough to Earth's orbit that the Earth itself, whatever remains of it, may not survive as a solid body, though some models suggest Earth's orbit could actually widen slightly as the Sun sheds mass during this phase, potentially letting a scorched, lifeless Earth narrowly escape being swallowed outright. None of this is presented as settled certainty. The precise details of the Sun's red giant phase and Earth's exact fate within it remain areas of ongoing research and legitimate scientific disagreement among solar physicists modeling the Sun's mass loss during that era. What is not in serious scientific dispute is the broad timeline. Whatever the Andromeda and Milky Way merger eventually looks like from the inside, no human being, and very likely no descendant of any currently existing terrestrial life, will be present on Earth's surface to observe it, because Earth's own surface will very likely no longer support the kind of chemistry that made observation possible in the first place, long before the merger reaches any dramatic stage. It is worth noting what the Sun does after the red giant phase as well, since it completes the picture of what stellar future the Andromeda-Milky Way collision will actually be witnessed by, if anything is witnessing it at all. After exhausting its remaining fuel, the Sun is expected to shed its outer layers entirely, forming a brief glowing shell of expelled gas called a planetary nebula, unrelated in name to any actual planet, while its core collapses into a dense Earth-sized ember called a white dwarf, which will then cool slowly over trillions of years, radiating away its leftover heat without any further fusion to replenish it. A white dwarf remnant of the Sun would very likely still exist, cold and dark, throughout the entire span of the Andromeda merger, an inert observer, if it could be called that, present for the whole event but incapable of any further activity. There is a strange and important lesson buried in that timeline, one that reframes the entire premise this account opened with. The question of how long it would take to cross Andromeda implicitly assumes a traveller who survives long enough to complete, or at least meaningfully attempt, the crossing. Every answer calculated so far in this account, from light's 200,000 years to a hypothetical relativistic ship's tens of thousands, is dwarfed comfortably by the 4 to 5 billion years before the merger even begins, which is itself dwarfed, in terms of what actually matters to any observer originating on Earth, by the roughly 1 billion years before Earth's oceans are expected to boil away. Any crossing of Andromeda framed around a human traveller or a human civilization spacecraft was very likely never going to happen, regardless of how the propulsion problem discussed earlier eventually turned out, simply because the traveller's homeworld runs out of time first. This is not offered as a grim conclusion but as an honest one, and it sharpens rather than undermines the value of the question. If no human traveller was ever going to make this particular crossing, the question of how long it would take stops being a travel planning problem and becomes something closer to a lens for understanding scale itself. How enormous galaxies are, how empty the space between stars really is, how differently time behaves for a traveller moving near light speed versus everyone left behind, and how patient the universe is with processes that unfold across spans of time no living thing was ever built to witness directly. The final chapters turn to that lens directly, starting with the strange, layered nature of the light that makes any of this visible from Earth in the first place. Return for a moment to that faint smudge of light near the constellation Cassiopeia, the same object the very first chapter of this account opened with. Everything explored since then, the true size of the galaxy behind that smudge, the true distance to it, the true difficulty of ever reaching it, the true nature of the merger already underway, sits invisibly folded into that one unremarkable patch of sky. Nothing about how it looks to the naked eye hints at any of it. It simply looks like a faint elongated haze, easy to miss, easy to mistake for something far less significant than it is. One detail about that light deserves particular attention because it connects everything this account has covered back into a single coherent picture. Most distant galaxies viewed from Earth show redshifted light, their wavelengths stretched toward the red end of the spectrum by the expansion of the universe itself, a phenomenon separate from and layered on top of the ordinary Doppler shift caused by an object's own motion through space. The farther away a galaxy sits, generally speaking, the faster the space between it and Earth is expanding, and the more strongly redshifted its light appears, a relationship first mapped systematically by the American astronomer Edwin Hubble in the 1920s, using exactly the same Cepheid distance measuring technique described earlier in this account, and still, a century later, one of the foundational pieces of evidence for an expanding universe. Andromeda breaks this pattern. Its light is blue-shifted, not red-shifted, because it is close enough and moving toward the Milky Way fast enough, roughly 110 kilometers every second, that its own genuine motion through space overwhelms the much gentler pull of cosmic expansion at such comparatively short range. Andromeda is one of only a small handful of galaxies in the entire observable universe close enough, and moving in the right direction, to show this blue shift at all. Nearly every other galaxy beyond the local group, no matter how it happens to be moving on its own, is carried away from the Milky Way faster than it could ever move toward it, simply because the space between here and there is itself stretching. That single quiet detail, an unusual color shift buried in light too faint for the naked eye to analyze directly, is the same physical evidence used to establish the merger timeline, covered several chapters earlier. It is worth appreciating how much has been extracted from something as simple as measuring a shift in color in starlight collected by a telescope. Not just a speed, but an entire multi-billion-year future for two galaxies, deduced from a single faint spectral line and decades of careful repeated measurement, refined further by direct imaging from the Hubble Space Telescope, showing Andromeda's actual sideways motion across the sky, a motion so small it was only conclusively measured in the early 2010s, despite Slipher's original blue shift measurement dating back roughly a century earlier. There is also a subtler point buried in the fact that this light takes 2.5 million years to arrive at all. The Andromeda visible tonight is not the Andromeda that exists right now. Whatever Andromeda actually looks like at this present moment, its stars, its structure, even its exact distance from the Milky Way, is unknown and unknowable until light carrying that information has had 2.5 million more years to make the same crossing every earlier photon has already made. Every observation of Andromeda ever recorded, from the earliest naked eye sightings by ancient astronomers, including the 10th century Persian astronomer Abd al-Rahman al-Sufi, who described it in his Book of Fixed Stars as a small cloud, to the most advanced modern telescope images produced by instruments like the Hubble and James Webb Space Telescopes, has necessarily been an observation of Andromeda's past, layered 2.5 million years deep, arriving continuously, patiently, indifferent to whether anyone is looking. This layered, delayed quality of astronomical light is not a limitation unique to Andromeda. It is true of every star and every galaxy a person has ever looked at every distance, always. Even sunlight is 8 minutes old by the time it warms a human face, and starlight from familiar constellations overhead is typically decades to centuries old, having left those stars before most currently living people were born. What makes Andromeda unusual is only that it is close enough, and bright enough, to be seen without any instrument at all, making it perhaps the most accessible reminder available to an ordinary observer that everything visible in the night sky is, in a very literal sense, old news, still arriving. With that idea in place, one final task remains: gathering every answer this account has produced, the light's 200,000 years, the spacecraft's practically infinite years, the traveller's relativistic thousands, and the galaxy's own 4 to 5 billion into a single honest close. 11 chapters ago, this account opened with a question that sounds like it should have one clean answer. How long would it take to cross the Andromeda Galaxy? It does not have one clean answer, and by now the reason should be clear. The question quietly contains at least 4 different questions, disguised as one, and each of the 4 has its own honest, well-supported, entirely different answer. The first answer belongs to light itself. Light crosses Andromeda's roughly 200,000 light-year stellar disk in roughly 200,000 years, moving at the one true speed limit the universe enforces, unobstructed by the enormous emptiness that fills nearly all of that distance, since, as established early in this account, a galaxy's stars are separated by so many light-years of open space that a straight line through the disk encounters almost nothing solid at all. If the crossing is instead measured out to the full extent of Andromeda's dark matter halo rather than just its visible disk, that same figure could grow tenfold, to roughly 2 million years, a reminder that even light's answer depends on where the question decides the galaxy actually ends. The second answer belongs to any spacecraft built using real demonstrated human engineering. Using the fastest object humanity has ever launched, the Parker Solar Probe, at its peak speed of roughly 690,000 kilometers per hour, the same crossing would take on the order of 150 million years, and that number assumes a speed no current mission can sustain for more than brief periods near the Sun. Humanity's most distant actual traveller, Voyager 1, moving at its steady interstellar cruising speed, would need something closer to 3.5 billion years for the same distance. Neither number describes a journey any civilization, in any recognizable form, could plan around, and both numbers stand not as an embarrassment of current engineering, but as an honest measure of exactly how large the gap between planetary-scale spaceflight and galactic-scale spaceflight actually is. The third answer belongs to physics rather than engineering. A hypothetical ship travelling at a large fraction of the speed of light, perhaps 99.5% of it, would, from the point of view of everyone who stayed behind, still take a little over 200,000 years to complete the crossing, since nothing can move faster than light itself. But from the point of view of the traveller aboard that ship, thanks to the time dilation effect confirmed by more than a century of experiment, the same journey might be experienced as lasting only around 20,000 years, a full order of magnitude shorter, though still far beyond any human lifespan, and still requiring an amount of energy no known or seriously proposed propulsion technology can currently supply, energy on a scale comparable to minutes or hours of the Sun's own total output, simply to reach that speed in the first place. The fourth answer belongs to the galaxies themselves, and it is the only one of the four describing a crossing that is not hypothetical, distant, or bound by propulsion limits humanity has never solved. Andromeda and the Milky Way are already approaching each other at roughly 110 kilometers every second, and current research places the beginning of their merger at roughly 4 to 5 billion years from now, a merger that will unfold gradually over hundreds of millions of years through repeated gravitational passes that leave almost every individual star untouched. Even as the two galaxies' overall shapes are gradually reworked into something new, their central black holes eventually sinking together and merging in turn. This crossing needs no spacecraft, no engine, and no traveler. It is already happening, and has been happening, for as long as the two galaxies have existed within reach of each other's gravity. Each of these four answers is correct. None of them contradicts the others, because none of them is answering quite the same question, despite all four appearing to respond to the same 6 words. How long to cross Andromeda? What differs between them is not the physics, which is consistent throughout, but the identity of the thing doing the crossing and the frame of reference from which that crossing is being timed. Light does not experience time the way a human traveller would. A relativistic traveller would not experience time the way someone watching from Earth would. And a galaxy, vast enough to be measured in hundreds of thousands of light years, does not experience urgency at all. It simply continues along the gravitational path it has followed for billions of years, arriving eventually, without needing to hurry. And underneath all four answers sits the quieter fact explored 2 chapters back. None of them will ever be witnessed by anyone who asked the question in the first place. Earth's oceans are expected to boil away in roughly 1 billion years, long before even the fastest of the 4 crossings could plausibly finish, and the sun itself will have swollen into a red giant and cooled into a white dwarf ember long before the Andromeda merger reaches its own quiet conclusion. That is not a reason to dismiss the question. It is the reason the question matters at all, because a species capable of calculating an answer it will never live to see is doing something unusual, measuring a universe far larger and far more patient than the brief span of time it has been given to look up and wonder about it. What this account has really been about, underneath the specific numbers, is scale, the scale of a single galaxy, the scale of the gap between one star and its nearest neighbour, the scale of the energy required to move a single kilogram close to the speed of light, and the scale of time itself, measured not in years or centuries but in spans so large that an entire planet's habitable era fits inside them with room to spare. Andromeda will not wait to be reached by a human traveller, because it is already arriving on its own schedule, at its own pace, following the same patient physics that has governed it, since long before there was anyone on Earth to look up and wonder how long the trip might take. So how long would it take to cross Andromeda? Light takes about 200,000 years to travel from one edge of its disk to the other, a single unbroken beam moving at 300,000 kilometers every second and still needing 2,000 centuries to finish the trip. A spacecraft built with anything humanity has ever launched would need longer than the universe itself has existed, and even a hypothetical engine pushed to a large fraction of the speed of light would still cost its crew tens of thousands of years by the clocks of the people they left behind, whatever their own clocks read. And the galaxies themselves, the only travellers actually making this particular crossing, will finish in about 4 to 5 billion years, arriving not as a passage through Andromeda, but as a slow merging with it, one great spiral folding into another, until the disk that framed this whole question no longer exists in a form anyone could cross. Every answer is correct, and every answer describes a different kind of time, the patient, indifferent kind that light and gravity have always had, and the short, urgent kind that any living thing measuring it can ever actually spend. None of the 4 travellers in this account agree with each other, and none of them needed to. A photon does not know. It has taken 200,000 years to cross a galaxy. A galaxy does not know it has taken 4 billion years to reach its neighbour. Only a creature with a lifespan short enough to notice the difference could ever ask the question in the first place, which may be the strangest fact in this entire account. The very act of wondering how long the crossing takes is only possible because whoever is wondering will never live to see it finished. Look up at that faint smudge near Cassiopeia some clear night, if you get the chance. The light arriving in that instant left before there were eyes to receive it has already crossed 2.5 million years of empty space, and is, at this very moment, still arriving, indifferent to how long anyone standing beneath it has to wait.